we're extremely fortunate to have as our speaker Steve Kivelson, who received his PhD in physics from Harvard University in 1979, and is the Prabhu Gore Family Professor of Physics at Stanford University. His research interests have covered a lot of ground in this overall subject that we call condensed matter physics, but his current research primarily works on the theoretical characterization of this quantum world, which I just described. He's a distinguished member of our community with many honors, including membership in the National Academy of Sciences. Please join me in welcoming Professor Steve Kivelson. Steve.
Well, good. The microphone works. Well, thank you very much. Right. So I'm going to be talking about superconductivity and quantum mechanics at the macro scale, and I hope to explain to you what those words mean by the end of this hour. It's nice that this is sponsored by the Nick and Maggie DeWolf Foundation. I suppose all of the Aspen locals knew and loved the DeWolfs, but they were also very valued members of our physics community, and many of us experienced their warmth and hospitality and miss them. So discussions of science for the general public is fun and interesting, but there is a serious aspect to it. And so I hope you'll forgive me if I make a brief excursion discussing a political issue. So we've all become aware that many of the crucial issues facing our society in the world, modern world, have a technical component to them. Many such examples come to mind. Obviously, the response to the COVID pandemic, global climate change, management of the economy. Among these, there are some, in particular, where physics plays a role. Whoops, that wasn't one of them. But this is definitely decisions about investment in fusion energy research or research in quantum computing and quantum technologies. More generally, research involving visionary technologies often involves the input from physics, and exploitation of nuclear energy and research into nuclear waste management are also issues for which physics is important. Now, in that background, there is a serious problem, which again is often discussed, which is that there appears increasingly to be a loss of trust in scientists. And this is partly for a variety of societal and political issues that I won't comment on, not because I don't have opinions, but because I don't have any expertise. But it's also true that scientists have not been blameless in this. And so there are, in fact, many motivations for scientists in talking to the public to, let's call it exaggerate. There's a passion for getting it right for society, and the worry that if the message that we give about the science is in any way ambiguous, that that may undermine needed societal action. At a more immediate level, there's always the tension that explaining all the nuances and the caveats and the footnotes make it much harder to communicate the essence of the science, and therefore there is a great motivation to exaggerate. And finally, at the less grandiose level, well, there are benefits to the scientist in terms of maybe broader recognition and fame and glory, and maybe even higher levels of funding. So this is a danger in talking about such a beautiful topic as quantum mechanics. In my aesthetic judgment, and this is not a statement of science, but in my aesthetic judgment, quantum theory is the most beautiful and profound contribution of modern physics to human society. And with that background, my temptation to exaggerate is great. In particular, quantum mechanics is highly suited to mystical and seductive misrepresentations and distortions. There can be interesting analogies with quantum mechanics, but the direct connection between quantum mechanics and various philosophical stances is, at best, an analogy. And we've all come to be familiar with the quantum realm as a literary device which allows anything we want to happen, but in fact, the quantum realm does not allow us to violate the dictates of space and time or the second law of thermodynamics. And finally, again, more concretely, research in quantum information and quantum computing and various new technologies is a very exciting part of our field and is making spectacular advances which will certainly further our fundamental understanding of quantum mechanics and of the nature of the world, and will probably lead to technologies at some point in the future. But what that some point in the future is and what those transformative impacts are is highly controversial. I'm actually not an expert in this area, but I have many friends who are experts in this area, and their predictions, for instance, in timescales for laptop quantum computers range from 5 years to never. So my goal tonight is to share with you some of the tangible ways in which quantum mechanics manifests itself in the world that we can touch, that is to say, the world at the human scale, and I will hope to try to communicate to you some of the beauty and profundity of the topics without indulging in mystical analogies. So that's my goal tonight. And in particular, what I want to leave you with is the message that quantum mechanics is not just something that occurs in esoteric labs, but that it has consequences in spectacular, measurable, macroscopic phenomena. All right, so quantum mechanics. Quantum mechanics is the fundamental physics, the theory we use to describe physics at the micro scale. It's the theory that allows us to understand the structure of atoms, the nuclear physics of quarks and gluons and neutrinos and strings and all sorts of wonderful things. But it's generally thought that quantum mechanics is negligible for macroscopic objects such as baseballs and planets and universes. These are the regimes of Newtonian mechanics, of Maxwell's theory of electricity and magnetism, of Einstein's general relativity. These are all the realms of what we call classical physics. Whoops, what happened? Okay, so one way to understand whether the physics involved is classical or quantum is by seeing what fundamental constants of nature enter into the theoretical description of the phenomena that are being considered. So in classical physics, these constants of nature include the speed of light, which is usually represented by a small c, Newton's gravitational constant, which is typically represented by a large G, and some other things. In contrast, in quantum mechanics, Planck's constant, which is typically represented by small h, or sometimes by h bar, which is h divided by 2 pi, so it's basically the same thing. This is the fundamental constant that tells us that phenomena are quantum mechanical, and anything that we see in which Planck's constant appears is a consequence of quantum mechanics. There are other things. In quantum mechanics, we have a notion of fundamental particles which are indistinguishable from each other and thus have a single characteristic. For instance, E is the charge of the electron, and it's the same charge on every electron in the universe, and m sub e is the mass of the electron, which is likewise universal. So we're going to understand whether we're looking at classical or quantum effects by seeing what fundamental constants of nature appear. So the first thing I'm going to talk about is the stability of matter. And it turns out the stability of matter, the fact that you don't collapse, is a consequence of quantum mechanics. So we know that matter consists of positively charged nuclei and negatively charged electrons, and they're whizzing around each other in some complicated way. And in classical mechanics, these interact with each other by a Coulomb interaction, which goes like 1 over the distance between particles and is attractive between oppositely charged particles. And so what that means is if I take some typical configuration of positive and negative charges like this, it will have an energy density that's some minus number times the charge of the electron over the typical distance between particles. And this has the consequence that if I made the matter denser and denser, that is to say, if I make R smaller and smaller, the energy goes to minus infinity. So in classical mechanics, all matter would collapse. Now, the Heisenberg uncertainty principle is one of the most simple manifestations of quantum mechanics, and it brings in the physics of Planck's constant. What the Heisenberg uncertainty principle tells us is that the mean squared uncertainty in a particle's momentum times the mean squared uncertainty in a particle's position is always bigger than Planck's constant squared. This is one of the fundamental tenets of quantum mechanics. And so what that means is that if I squeeze particles into a small region, their mean squared kinetic energy, which is the mass, 1 over the mass times the momentum squared, is going to get bigger in proportion to 1 over r squared, because the momentum squared gets bigger the smaller the distance. And so in quantum mechanics, as a function of the density of matter, there is a term which is positive and proportional to 1 over r squared. This energy is minimized when the particles are as far apart from each other, and diverges, that is to say, goes to infinity, if the particles get too dense. So what happens in matter is that there's a balance between the classical forces that want matter to collapse and the quantum forces that want matter to fly apart. And as a consequence of the balance between those, we get some typical quantum of density of matter, which is given by this combination of fundamental constants of nature. It involves the mass of the electron, the charge of the electron, but most importantly, it involves Planck's constant to the 6th power. And if we evaluate this quantity, we get a number, 5 times 10 to the 22nd particles per cubic centimeter. And lo and behold, this allows us to understand the density of matter, the density of you and your chair. Here, I looked up the density of crystalline sodium, carbon, sulfur, tin, iron, lead. With no work, we can understand not the small differences between these, but why all of these are approximately equal to the quantum of density. Okay, so this is the first and most broadly appreciable macroscopic consequence of quantum mechanics. But it's not so vivid. So let me go to my second example, which is ferromagnetism, that is to say permanent magnets, something that undoubtedly all of you have encountered. So we learn in high school physics that magnetic fields are produced by circulating currents. So somehow, somewhere in a ferromagnet, there are currents going round in circles that are producing the magnetic fields of the ferromagnet. But the startling question is, what keeps those currents going? Currents, we know, tend to decay. We need batteries to drive currents. But in a ferromagnet, these little loops of current that are responsible for the ferromagnetism keep going without any battery. I'm going to make one technical aside. I'm not going to explain this, but it actually turns out that in classical physics, there really is no magnetism. Any effect you see that involves magnetism is, in a very precise sense, a consequence of both quantum mechanics and relativity. In fact, we'll see that when we discuss magnetism, the quantities that we're discussing will involve not only Planck's constant, but also the speed of light. Okay, so let me think about ferromagnetism in the following way. We're going to, after this lecture, show various demonstrations with levitation. So I'm going to illustrate what's so peculiar about ferromagnets by thinking of ferromagnetic levitation. So here I have a cartoon of some container. The blue is supposed to be some container. And in it, I put two ferromagnets, one with its north pole pointing up and the other with its north pole pointing down. And maybe you've learned that north poles of magnets repel each other. So because they repel each other, this magnet is not going to come crashing down. It's going to remain levitated above the magnet below it. The more detailed way to understand this is that the magnet is a source of magnetic fields. Magnetic fields lines leave from the North Pole and enter to the South Pole. And now, if I tried to squeeze this ferromagnet down on the ferromagnet below it, I would be compressing these magnetic field lines. Of course, I can't see these magnetic field lines, but they're there, and compressing them costs energy. And so this ferromagnet will float above that ferromagnet, and it will stay there forever. I don't need to connect this to a battery. Now, the forever isn't really quite as good as it could be, because if somehow this upper ferromagnet managed to wiggle around and flip so that now the South Pole was down, well, now a South Pole and a North Pole attract each other, and so this thing will come crashing down. And in terms of magnetic fields, that's because the magnetic field lines go from the South Pole to the North Pole. So when I crash this down, I get rid of all the magnetic fields, and the energy of the system goes down. So while this magnetic levitation is stable without a magnet, I do have to keep the boundaries so that it doesn't flip around. Okay, nonetheless, it's quantum mechanics that's responsible for those persistent currents in the ferromagnet, those persistent orbits that produce the magnetic field that produce ferromagnetic levitation. All right, now I'm going to go to the star of the show, which is superconductivity. So before I get to superconductivity, I need to talk about regular conductivity, that is about passing a current through a metal. And passing a current through a metal is described by Ohm's Law. Ohm's Law says that the voltage necessary to pass a current is proportional to the resistance of the metal. Or put another way, if I want to keep a current going through a piece, wire of metal, there is an amount of power I'm going to have to provide to the system, which is the resistance times the current squared, and the fact that you can't get something for nothing is, in physics called the second law of thermodynamics, means that R is always a positive number. It always costs energy, costs power to keep a current going. Okay, so this is a picture of Ohm's Law. You don't get anything without working. Okay, now, if you take a typical metal, here I'm plotting the resistance of some metal as a function of temperature, and what's often seen is that as you lower the temperature, the resistance of the metal gets smaller. It becomes easier to pass current through a metal. If it's colder, it requires less power to keep it going. But some metals, as you cool them, the resistance goes down, and then at some very special temperature, called the critical temperature, the resistance drops to 0. This was discovered in 1911 by Camerlionis. That's Camerlionis. This is his data on mercury. This temperature here is 4.2 degrees. That means 4.2 degrees Kelvin. That means 4.2 degrees above absolute zero. That's something like minus 455 degrees Fahrenheit. At this temperature, everything except helium is a solid. Air is a solid, you are a solid, I'm a solid. Nonetheless, below this temperature, he saw that the resistance of mercury, which was steadily decreasing, suddenly drops to 0. Now 0 is an abstraction. 0 is something that's understood by mathematicians, but physicists talk about measurable quantities, and so you should ask me, what do I mean by 0? And of course, 0 means smaller than anything that I can measure, but how good am I at measuring? What does 0 really mean? So the way we can see how good 0 is by considering something called a persistent current. So what we do is we take a ring of superconductor and we start a current going around in a circle around this ring of superconductor. And of course, as we've already mentioned, if we have current going around in a ring, it means we're going to have some magnetic field, which is produced by the current going around in the ring. And the strength of this magnetic field will be proportional to the magnitude of the current that's going around in this ring. And then what we do is we measure the magnetic field, so implicitly we measure the current, and we measure it as accurately as we can, and then we go away and wait as long as we have patience, maybe the lifetime of one graduate student, and we come back and we measure the magnetic field again, and we ask, how much has it decayed? And the answer is within our most accurate measurements and with our longest patience, it hasn't decayed at all. That is to say, within the error of our measurement. So then we ask ourselves, suppose it was decaying at the fastest rate it could be decaying and escape our detection. How long would it take for the current to decay away entirely? And the answer is longer than the life of the universe. Okay, so I hope you're impressed. This zero, this is a really serious zero. Okay, so here's what we've learned about superconductors. Superconductors are metals above some critical temperature, and below that critical temperature, they enter a new state of matter, and this is observed in many materials. And below that temperature, the resistance is zero. The superconductor can support a persistent current. Now, there are other features of superconductors. They are perfect diamagnets. That is to say, they expel magnetic fields. Superconductors don't like to have magnetic fields in them, and left to their own devices, they will send a magnetic field that you try to put in, it will move them out. I'll explain that in a minute. And they also exhibit something called macroscopic coherent quantum behavior, flux quantization, and the Josephson effect. And I'll discuss both of those now. So, let me start with the Josephson relation. So another fundamental piece of quantum mechanics, actually the first piece of quantum mechanics, the first quantum mechanical relation was written down by Max Planck, and he said that the energy of some object is equal to Planck's constant, that's how it became Planck's constant, times a frequency. A frequency is if we have something changing in time and it's oscillating, the frequency with which it changes, revolutions per second, is the frequency. So the Josephson relation is a macroscopic version of this. So what does that mean? We take two pieces of superconductor, here shown in blue, and we make a junction between them, shown in pink. And then we apply a voltage, V, across this junction. And what happens when we do that is a current flows. But surprisingly, the current, even though the voltage that we've applied is a constant, the current that flows is time dependent. In fact, the voltage that flows oscillates with time, and the frequency with which it oscillates is related to the voltage. It's linearly proportional to the voltage, and the proportionality constant is twice the electron charge divided by Planck's constant. This is, in fact, nothing but this Planck relation. 2E times V is the energy required to take two electrons across this voltage, and then that's equal to Planck's constant times the frequency of this oscillation. Now, by now, I hope you're suspicious of me, and when I say equals, you say, what do you mean by equals? How precisely is this equality satisfied? And the answer is, it's exact. And the reason it's exact is it's known with more accuracy than we know how to measure the voltage. In fact, this relation is now used as the definition of the volt. So this relation is definitionally exact. But that's an unsatisfactory answer. So what we can do is the following. We can take two Josephson devices, we can put the same voltage across them, and we can ask, do they both oscillate with the same frequency? Or, in particular, can we detect a difference in frequency between the two oscillations? And the answer is we can't. And the accuracy with which that's been established is now better than 1 part in 10 to the 17th. Okay, 1 part in 10 to the 17th is a number that's impossible to understand, so let me try to give you some understanding of it. So I looked up in preparation for this talk what the US GDP was in 2021, and it said it was roughly $23 trillion. But if I wanted to know this number to an accuracy of 1 part in 10 to the 17th, it would mean I would need to know the US GDP to within the nearest 100th of a cent. Okay? I mean, that's really precise. Okay, so let me talk a little bit about this Meissner effect, the expulsion of magnetic fields by superconductors. Although you didn't know it, we've already discussed it. So here's our superconducting ring, and as we said, the superconductor, the current that's going around in our superconducting ring produces a magnetic field, and we've already determined that the current doesn't decay, which means the magnetic field doesn't decay. Why doesn't the magnetic field decay? Because in order for the magnetic field to decay, magnetic field lines would have to move from inside this ring to outside this ring. And in order to do that, they would have to go inside the superconductor. So this persistent current was actually a measurement of the Meissner effect. But once we start looking at this, we discover another remarkable macroscopic quantum phenomenon called flux quantization. So the flux, which I've indicated by this Greek symbol capital phi, is the total integrated magnetic field through the ring. That is, notionally, it's the number of magnetic field lines through the ring. And what one observes is when one makes superconducting rings like this and then measures how much flux there is through them, that the flux you see is always equal to an integer times this quantity, which is called the quantum of flux. It's Planck's constant, so it's a quantum mechanical effect. It's the speed of light, so it's a relativistic effect, divided by twice the charge of the electron. Okay, and so this is something you measure easily, and it's macroscopic, and it involves quantum mechanics. There is a messy version of this same thing, which will be important for the demonstrations. So although it's conceptually a little bit more messy, I'm going to spend a minute describing this, which is the following. So suppose I took a piece of superconductor, but it was at its temperature above Tc, so it's a metal, and I put it in a magnetic field, so magnetic field lines penetrate it. And then I cool it down below its transition temperature. What's going to happen? Well, the superconductor is going to want to expel the magnetic field lines as best it can. So as best it can will be, it will confine them to, say, defect regions where the superconductivity is somehow weaker, and there will be flux quanta going through at specific places. And then once I'm in the superconducting state, these flux bundles can't move. So strangely, what happens in the superconducting state if there are magnetic fields penetrating is that the magnetic fields are pinned inside the superconductor. Even if I take this superconductor out of this magnet, those magnetic field lines will remain pinned there. So when we look at demonstrations, I want you to imagine that when we have superconductors with magnetic fields, they have these strings coming out of them, and they're connected to wherever the magnetic fields are connected to, and we're going to see the effects of those strings. Okay, and so, for instance, this will give rise to magnetic levitation. This is a picture of something that we'll show, that you can see if you come up at the end of the lecture. This is a piece of a superconductor. It's sitting above these magnets, and it's stably levitated, because if it tries to move down, the magnetic field needs to become stronger, and it doesn't like that. If you tried to pull it away or slip it off to the side, the magnetic field will want to become weaker. You can't see them, but there are magnetic lines here that are pinned in this superconductor that are holding this superconductor in place, levitating. So this is pretty wonderful. Why don't we have superconductors all over the place? And the reason is that until 1986, the highest temperature superconductor became superconducting below low enough temperatures that air is a solid. It's really expensive and complicated to make things that cold. In 1986, high temperature superconductivity was discovered. Now, high temperature superconductivity is sort of a physicist's joke. What this means is that materials were found that are superconducting at such balmy temperatures that air is a gas. But it's still colder than any temperature in any room, even on top of Aspen Mountain. So here's Camerlionis's data. This is 4.2 degrees Kelvin. This is the high temperature superconductor YBCO. High temperature superconductivity was first discovered by these two gentlemen, Bednorz and Mueller, for which they received the Nobel Prize. But their high temperature superconductor was substantially lower than this high temperature superconductor, which was discovered by this person, Paul Chu, who did not win the Nobel Prize for it. And what you can see is that the critical temperature here is 90 degrees above absolute zero. And that's significant because liquid nitrogen boils at 77 Kelvin. So above this temperature, air is solid, or at this temperature, we can use liquid nitrogen to cool our superconductors, and that's what's in here. Liquid nitrogen is as cheap as beer. So I wanted to discuss some of the history of the discovery of these materials, but I see I'm going a little bit behind, so I'm going to skip this. This is a chronology of materials discovery and how the critical temperatures have changed with time. This is another version of that. This is this important boiling point of air. This is a picture of the crystal structure of one of these high temperature superconductors. Okay, you can ask me about these slides later. This is a little bit more interesting. This is a picture of a piece of this high temperature superconductor, YBCO, yttrium, barium, copper oxide. And there are a number of things that you notice about it. One is it doesn't look much like a metal at all. And that's correct. Metals at room temperature tend to be shiny. This is black. It looks like a piece of ceramic. In fact, it's a really crummy metal. It's so crummy that we call it a strange metal. But this material is the best superconductors. And these pictures that I showed you were possible only because this is a high temperature superconductor which has been cooled with liquid nitrogen. Okay, so since I wasn't able to have you come close in large numbers and we weren't able to set up a video, I thought I would show you the demonstrations, or better versions of the demonstrations, that I would like to show you of superconducting levitation. So this is a video I got from a colleague, Matthew Sullivan at Ithaca College, and I think it's a rather charming video that shows the demonstration that I would have liked to have showed you. Whoop. How do I get it to start? There we go. So here he's showing you a puck of this high temperature superconductor, yttrium, barium, copper oxide, and commenting at how it's not shiny, and it's not ductile, and it's not even strong. But it has a superconducting transition temperature, which is a balmy 92 Kelvin, 92 degrees above absolute zero. There he's putting liquid nitrogen into a cup and putting a puck of YbCO in that puck. In that cup, the puck is surrounded by something to help keep it from heating up. And there you can see that it's being levitated above a ferromagnet, but you can almost see the magnetic field lines coupling this to the ferromagnet. Not only did it levitate, but it lifted up the ferromagnet. Here, he's made a track made of magnets, and his little puck of high-temperature superconductor is levitating at a fixed distance above the track. Again, I hope you can, in your imagination, see the magnetic field lines that are trapped in that puck of superconductor and then are going down to the magnets below. One thing that you notice is that as the puck warms up, it will eventually stop to be superconducting, and then it will no longer levitate. Okay, so, well, this is pretty cool. He proposes that a near-term application for high-temperature superconductors is better roller coasters. Okay, so joking aside, one would like to end such a talk with a discussion of all the practical wonders that are going to follow from advances in superconductivity. I have to say that I deeply believe that they will, but as is common with advances in fundamental science, it's very hard to say when or in what way. So one thing that people certainly think about is that superconductors should be good for power transmission lines. You could send currents through without any loss. I think it's pretty clear that although that sounds good, that's unlikely to ever be the case. Power transmission is an economic issue, not a physics issue. But superconducting interconnects in computers sounds very reasonable, at least to me. Superconductors for all sorts of precision technologies, and if there are going to be quantum computers, then superconductors will certainly be a part of them. There are a number of actual uses of superconductors that are widespread even today. What's probably most familiar to you is magnetic resonance imaging, MRI machines, which are possible only because of the superconducting magnets. And so these are a very beneficial and widespread use of superconductors. They're also used for the magnets in any big particle accelerator, such as the Large Hadron Collider, the LHC. They're apparently used in the generator coils in some very big windmills. All current attempts at fusion using tokamaks use superconducting magnets. And, well, what's for sure is that they allow cool demonstrations. So, of course, the Holy Grail would be a true room temperature superconductor, so we wouldn't have to do all of this refrigeration. Well, we're looking, we still hope, but as far as I know, the only clear place where room temperature superconductors have been found is in the Hallelujah Mountains of the planet Pandora, where these mountains levitate, presumably because they're rich in the unimaginatively named high room temperature superconductor unobtainium. Okay, and for those of you who don't know, this is from a movie from some time ago called Avatar. So, good. I'll answer questions, and then once the questions are over, if people are interested, we have demonstrations here of both ferromagnetic levitation and superconducting levitation. But if you come to see them, please stay social distanced and keep your masks on and do things so that the management here won't get upset with us. All right, so I guess then I'll stop.
Thank you, Steve. We have time for questions or comments.
So I've noticed with superconductors that while a magnet might levitate on them, they're not actually magnetic. Like if you put a piece of metal next to them, it doesn't stick. Why is that?
That's right. So
Steve, can you
yes.
repeat the question?
So the comment was that there's a big difference between the ferromagnetic levitation and the superconducting levitation. In the ferromagnetic levitation, the two things are both magnets. You bring them up to anything else, you bring them up to a nail, and they'll pick up the nail. Whereas with the superconducting levitation, the top piece, no, what did I do? Yeah, the bottom piece in the pictures that I showed was a ferromagnet, and I could see that it was a magnet by going around and picking up pieces of nail. But the superconductor by itself was not a magnet at all. If I brought this piece of superconductor next to a nail, the nail would ignore it. And so that is a very different thing. So what the ferromagnet does is it makes magnetic fields, whereas what the superconductor in this particular configuration does is trap magnetic fields. It's not making its own magnetic fields internal to it, but it's trapping the magnetic fields that we initially imposed on it. And then once I've done that, then it is magnetic. And so if I took a superconductor with trapped flux in it and then went near your nails, well, I would freeze my hands. But if I did this in some way that I didn't have to touch something at liquid nitrogen temperatures, then indeed I would see that I would get a magnetic response. It would be an induced magnet in that sense. So very nice question.
Okay. I think there was, yeah, please.
Yeah, at the beginning you said that what this was going to show is that quantum mechanics, there are these quantum mechanical effects that we can see, which are ferromagnetism and superconductivity. So I guess what you're saying is that ferromagnetism and superconductivity can only be explained if you include quantum mechanics in the explanation. They can't be explained classically. So I'd like to understand what it is about ferromagnetism or superconductivity or both that's quantum mechanical.
Okay, so I actually said, thank you, that's going over the logic is really helpful. So I said two things. So one is, the general thing I said was that without quantum mechanics, you couldn't understand the stability of matter, you couldn't understand the existence of ferromagnets, and you couldn't understand the phenomena of superconductors. Okay, so I'll come back to why I said that. I'll try to reiterate that. But with the superconductors, there was something even more direct. So what I said in the superconductor is that I could see for a voltage that you measure, so you measure a voltage, you measure a frequency of the oscillation of the currents. These are two things that you do, one with an ohm meter, one with an ammeter. Okay? And then you take the ratio of these two things, and you see that the ratio of these two things is equal to twice the charge of the electron divided by Planck's constant. So you've measured Planck's constant in this macroscopic measurement. So regardless of what you thought the theory was, you know that you're seeing quantum mechanics because the thing you're seeing is quantitatively dependent on Planck's constant. Okay, so that's the most direct manifestation of quantum mechanics macroscopically, or similarly, the flux quantization that I described, that the flux through a superconducting ring is an integer times hc over E, Planck's constant times the speed of light over E. So knowing just these fundamental constants of nature, I can tell you exactly what the flux is going to be through a superconducting ring, and since I need Planck's constant to do that, I know the explanation, whatever it is, must be quantum mechanical. Okay? Thank you.
Okay. Any other, before I get back to you for the second question, any other questions or comments? Yes, there's a hand over there, please.
If you have a permanent magnet and you place on top of it a material which is both a ferromagnet and a superconductor, which one would win? If you turn it around so that the poles face each other, would it behave first as a superconductor and levitate, or first as a magnet and go down?
Are you thinking of applying to graduate school? That's a really good question. So first, one of the...
Maybe Steve,
What?
you can repeat the question.
Yes. So the question is, suppose I had a material that was both a ferromagnet and a superconductor. I'll go on to the second part of the question, but that first part of the question is super interesting. It was thought for a long time that no material could be both a ferromagnet and a superconductor. But now we know that this is possible, and it's extremely exotic, and it's something that we're grappling with, understanding it. So that was a good question. Now, the second part of the question was, which would win? I told you that without the confining barriers that keep the ferromagnet from flipping over, that ferromagnetic levitation is unstable, because if I had a puck of ferromagnet with its north pole up and a puck of ferromagnet with its north pole down, and I didn't have the constraints, and I let it go, the ferromagnet would simply go whoosh. Okay, so now the question is, if we have a puck that's both a ferromagnet and a superconductor, would it flip and crash, or would it continue to levitate? So certainly it would flip. It would want to have the ferromagnetism, the north pole of one next to the south pole of the other. Certainly if the ferromagnetism is weak enough, it would continue to levitate, but I don't know exactly what would happen as we change the relative strength of the superconductivity and the ferromagnetism. Maybe somebody in the audience knows.
That's a thesis topic for his
Yeah, that's your thesis topic.
Any other questions, comments? Yeah, so please.
So you talked about how to determine if it is truly zero, if or it's just astronomically small, that you put a current through it and it generates a magnetic field, and then you detect the magnetic field. Is that right?
Yes.
But you say it's not magnetic, or you can say some superconductors would be induced by magnet.
No, so you might ask, how did I get the current going in the ring? Okay, so there are many ways that I could do that, but one is I could start with the current going through the ring and the temperature above the critical temperature. So it's just a metal, so I would get the current going around the ring by attaching it to a battery. Okay, and then I would cool it down below Tc, and then I'd remove the battery. Okay, and there would still be some current going around the ring. So I've prepared it that way, and once I've prepared it that way, there will be magnetic flux through the center of the ring. And so there's history. Exactly how much current there is going to depend on how much current I drove through it before I cooled it down, and how I cooled it down, and how I detached the battery. But once I've set the system up so that I have the current going around the ring, and I have the magnetic flux through the ring, that situation will remain forever.
And is that the way that you would measure the resistance in any superconductor? Or is that
Well, so the resistance, that's the best way to measure zero. I mean, we could also, hook up an ohm meter to it and see that the resistance is 0, but the accuracy of that measurement would be much less than the accuracy of this persistent current measurement.
Okay, I think this is probably a good place to stop. So several things. First, please join me in thanking Steve for this wonderful lecture.